Okay, kids, here we are. Let's learn a little bit about work and potential energy in a capacitor. Now, we've already learned a little bit about capacitors. And I've shown you my bad Larry capacitor here. Where'd it go? Here it is. Ah, this is like, whoa, capacitor. You don't want to mess with this bad Larry here. Boom. We also have smaller capacitors. This capacitor here is actually like the same size as a battery. Here's a battery, a capacitor, look, same size. And I unraveled it, so it was actually around the same thickness as well. And I unraveled it many times, and you can see that what you get out of it is two thin pieces of aluminum separated by what looks like, in this one, like cellophane. All right, check that out. Check it out, check it out. And now, so we have now what's called a parallel plate capacitor. This is now parallel. These two plates of aluminum are very, very thin and separated by a little bit of, like I said, that cellophane-looking material. And so what you end up getting is two pieces of aluminum separated by a dielectric in that particular one. It's, a dielectric. Again, I think it's cellophane, but can't tell. It's just too thin to even look at it, really. So it is dielectric. Dielectric can be any material. Actually, it can be dry air. Dry air is actually a decent insulator. So it can be dry air, glass, plastic, something to keep the charge from one side of our capacitor separated from the other side of the capacitor, because you don't want the charge to discharge until you want it to discharge. You need the capacitor to be ready to do what you want it to do when you want it to do it, all right, and not before then. So the dielectric is in the middle. Now, just kind of quick review. I know you all watched that video on capacitors, which is actually well done, very well done. That person can certainly do all that drawing and animation stuff quicker than I can do it on the board, so watch it. It's a good one. But this one also, I just want to quickly go over that we have a battery. Here's a little positive, bumpy parts positive, negative, connected up. And that's how we get the capacitor to get charged. The negatives here we go. Yeah. So the positive side. So the electrons that are in the metal are attracted to the positive, so they move out of this piece of metal here, going toward that positive electrode here. This is the cathode, and the anode, we have the negatives. And those negatives in this part of the battery say, ooh, I don't like you negatives coming in here, so I'm going to run away over here, and this plate becomes negatively charged. And eventually it doesn't continue forever, it does stop. A battery can only get this capacitor to be charged so much, depending on the voltage of the battery. So if we have eventually these electrons which are running away from here saying, oh, I like you, then they get about halfway here and they go, wait a minute, this is positive and I like you, but you're positive as well because we all left and now you're positive and now we kind of want to go back and I'm not going, oh no, hey, what do we do? I like you, so much indecision, torn between two lovers. Yeah, and so the electrons will eventually go, and they'll stop flowing. All right, so when we get that stoppage of flow, okay, we can disconnect our battery, and these two plates will stay charged, unless made to discharge of some way. Like maybe you put a wire between them and discharge them, or maybe you can put a switch between them and discharge them with a wire. And when you're ready to use them, you use them. Okay, well, anyway, let's get into the work and the potential energy in the electric field created. Now, we all know that electric fields are out of the positive and into the negative. So if I were to draw my electric field between these two parallel plates of my capacitor, it would look like this, arrows going down. Oh, that's because that's like gravity, the direction of stuff like gravity. No, doesn't have anything to do with that. I could have made this the positive and this the negative up here plate, and I would switch the field direction. So no, it's not due to gravity. It's due to the fact that if we were to take a positive test particle and place it in that field, it would be attracted down. That's the way it was defined, is what would happen to a positive particle in the field, the direction of the field lines. And so that particle will go from here to there. Now, by definition, the positive end, the positive area is called the high voltage side of the field, and the negative side is called the low voltage side of a field. And that has to do with the test particle. The test particle up here wants to get down here, and if the test particle here wants to get down here, then there's a high degree of voltage because it wants to go from here. Now, if you're down here where you want to be, that'd be low voltage. It's kind of like the same thing as with gravity. Let's think back to gravity. Gravity is a good analogy to use when it comes to electricity. So if we have this marker here, and it doesn't want to be here, it wants to be down there. So what do we have? We have a relatively high potential energy here. This says, I don't want to be here. I want to be down there on the floor. Now I'm on the floor. I'm happy, yay. But how much potential energy is there down there? None, because you're where you want to be. So if something's where it wants to be, there's no potential there. If you're away from where you want to be, there's potential. You have a lot of potential, kids. Yes, you do. Yes, you do. Yes, you do. Oh, good kids. Now, let's go back to so the positive particle. Let's go back to this now. The positive particle doesn't want to be here. It wants to be here. So there's high potential. Remember what voltage means. Voltage means electric potential, or potential difference. The difference in potentials give us a voltage. And those are different words. It's another thing we gotta be careful of. Sometimes you'll be asked about electric potential or potential difference. I want to throw another one in there. EMF, electromotive force, EMF. That one comes out once in a while. They all mean voltage. All of those different terms mean voltage. And that means we have a high potential here because it wants to go here. And it's not there, and that's where it wants to go. Now, if this got down to there, then it wouldn't have even more potential. It would be low potential because it's where it wants to be. Does that all make some sense? I'm sorry, I'm going fast. I got coffee before I started this video, and whoa! All right, sorry. Rewind. Oh, yeah, play at half speed. All right, so now, let's go back and say, okay, so just be aware that the area of positive is called high potential, the area of negative called low potential, because of what a positive particle will do if it was in the field. Everything's based on a positive particle. So let's say that we had, now the term, sorry, it's not COVID. The term high potential and low potential is the potential difference between positive plate and negative plate. So let's say that this was a 30 volt field. From here to here, the difference in potential is 30 volts. I'm just making the number up. Where'd you get that from? I just made it up. So now that would mean that from here to there, we have a difference of 30 volts. And it doesn't matter what this, you could say that this is 45 volts, and this down here, all right, is 15 volts. You have a difference of 30 volts. You could say that this plate up here is 30 volts, and this plate down here is 0 volts. The difference is 30 volts. It doesn't matter what the voltage of this one is and this one is, as long as they're different by 30 volts. So it doesn't make any difference. I mean, it would be kind of like if I took this marker and held it here and said there's some gravitational potential energy, 50 joules of energy. Okay, so 50 joules between here and down there. Now down on the floor, it doesn't have any potential energy anymore. It's gone. So you could say it has 50 and 0 down there. Or you could say, because this is America and you can do it, this has 100 joules, and on the floor it's 50 joules. Difference is 50. It doesn't matter as long as there's a difference of 50, because that's what you have. And that is, it's kind of like a gravity analogy of voltage. So let's go back to our parallel plate capacitor here. So you remember the positive is your high voltage, the negative is your lower voltage, and a positive particle wants to go from here to here. Now when we get down here, no more voltage, no more potential. All right, now, if let's say I get the positive particle down here on the bottom plate, and it'd be kind of like I bend over and I pick up the marker, right? And if I want to do that on a big, whoa, that was exhausting, kids. You have no idea how heavy this thing is. And I had to lift it like 1.5 meters. I'm done for the day. No, just kidding. Just kidding. Oh, just kidding. Had my Cheerios this morning. All kinds of energy. So now if we wanted to move this positive from here to there, where it doesn't want to go. It doesn't want to go up here. It doesn't like that positive. Positive don't like positive. Likes negative. But let's just say we're going to do it. We're going to move you up here. No, we'll do a different marker. We'll stand out a little bit here. I don't want to do it. You can't make me. No, you can't make me. No! Yeah, just made you. All right, so there we go. We move that positive down from here to here. Work has to be done. It's not going to do that on its own. It doesn't want to be there. So I got to do some work. So if I'm going to do work on this, okay, I have to do work to lift the marker off the ground, and I'm exhausted. Okay, we have to actually physically get this bad Larry here from here. It doesn't want to go there. So that's work being done. That is work in an electrical system. Now, work and potential energy and kinetic energy are all interchangeable. They're all related. Anybody in Physics 1 knows this. If you're just a Physics 2 person, you haven't had Physics 1, well, here you go. Learn it right now, that the potential energy and kinetic energy and work is how we get potential to become kinetic, and kinetic to become potential, that's called work. Work is the way we get energy to change. Okay, still with me? Stick with me now, come on. Stick with me. So I can get I can get potential to become kinetic, and kinetic to become potential by having work done on or by a system. So if I want to get this particle to move from here to there, it doesn't want to go there, so I have to do work to do it. Get up there, get up there. Again, I'm exhausted. So I got this moving up here because I did work on the particle to give it potential energy, and if I let go of it, it'll turn into kinetic energy to get back to where it wants to go. These are all interchangeable. All right? Okay, so now let's look at our equations for work and potential energy. Potential energy in an electrical system is QED. That's analogous to in a gravity system, which would be mgh. So QED. This part of it right here is called voltage. That ED is called voltage. All right, Q, so what do we get? We get PE equals Q times V. And that's potential energy. So if I want to give a positive particle sitting on a negative plate some potential energy, what I do is I do work, lift it to here, and now it gets potential energy. So the potential energy that it gets from here to there is the work that I did. So that means that this equation also equals work. Work done by or on a positive or a negative particle to get it to go where it doesn't want to go. You got to do work into it. You got to do work on it. So getting work done on the particle to go from here to there, I can do that. Now work is equal to the potential energy that the particle gains. So down here it has zero potential, zero PE. It's where it wants to be. I do work on it, I get it to here, now it has some potential. And I'll give it 10. 10 PEs, which by the way, between joules, energy we're measured in joules. So now what did I have to do though? I had to do work on it. We had to do 10 joules of work to get it from here to there into a position where it now has 10 joules of potential energy. All right, and then of course we could let go of it and go flying back down, turn into 10 joules of kinetic energy, lather, rinse, and repeat if I lift it back up again and let it go. So the potential energy of a system, okay, our system being a positive or negative particle in a field, is going to be equal to the work done on that positive or negative particle. Okay, so here is an equation. Oh, and by the way, this is voltage, E times D. Voltage is the amount of joules per unit of charge. Okay, basic joules per unit of charge. Not total joules. Total joules is your potential energy. That's your total joules. So if you take the amount of total joules and divide it by the charge that you put in the field to get the total joules, you get voltage. You get joules per charge. So this is voltage. So we'll write that equation down. All right, voltage is this is electric field, which is newtons per coulomb, and this is distance, which is in meters, and Newton meters. Okay, that's joules. Newton meters is joules per coulomb. So that is our joule unit. All right, so that kind of goes through a little bit of a capacitor review about capacitors, and then about field in a capacitor. And if we want to move a charge through a field, we have to do some work, and our equation for work is equal to the same thing as potential energy, and the potential energy equation comes from our potential energy equation up here, which is QED, which is V is V, that's V is V, blah, 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 we get voltage. Whoa! We just covered a whole bunch of equations there. Oh, all right, okay, I'm exhausted. This is almost a 15-minute video. I need to go get some more Cheerios because I did so much work. Okay, kids, we'll see you soon.